Hello everyone, this is Shubhajit Povnik from Team Cubalytics, comprising of Mr. Klaus Seifert and myself from Germany. And today, in the next 10 minutes, we are going to walk you through our solution for the water leakage detection and localization challenge as a part of our participation in BattleDam 2020. We start with a brief background, followed by explanation of each step taken to solve the problem. We'll then have a look at our analysis of 2018 and 2019 data. And before we finally conclude, we briefly explain why we selected a deterministic approach over a probabilistic one. As the network comprises of 905 links or pipes with a total of 119 sensors to detect demand, pressure, flow, and level, our fundamental assumption is that a leakage in any pipe within the network will reflect incongruity across the nearest located sensors at either end of the leaked pipe. We combine principles from two worlds, data science and hydraulics engineering, to develop our solution. Before we proceed with explaining the steps, please note that the numbers and names referred here onwards are for illustration purposes only, as it would have been visually challenging to accommodate the real matrices of such high dimensions in the following slides otherwise. So, let us consider T1, T2, T3 through Tn represent the timestamps, while P1, P2 through Pn indicate the link IDs or the pipe IDs within the network, and C1, C2 through Cn characterize the various sensor node IDs, which are essentially the column names in the matrix. We wrote a program in Python which would detect the nearest located sensor at either end of a pipe within the network. For example, in this illustration, for this leaked pipe Pn, which is highlighted in gray, as we propagate to its left and right, we identify the nearest located sensors as CL and CR respectively. And we applied this algorithm to each link within the network to store the mapping of all pipes to their respective nearest located sensors in memory to what we call the in-memory master map. Next, we combined all the readings of the different files that were provided to us, which comprised of the readings of demand, pressure, flow, and level sensors by timestamp to form one single matrix. And this we considered as the master data set. In our next step, we used statistical methods to identify the anomalous data points within this matrix and converted the entire dataset into a binary matrix, where the ones fundamentally represent the anomalous data points and the zeros represent the normal sensor readings. We then reduced the dimension of this matrix by removing all the rows with zero values, implying removal of all the timestamps that did not record any irregular reading, indicated in gray as you see in the illustration. And this matrix that we finally derived was coined as the anomaly matrix, on the basis of which we identified and localized leakages. In our next step, we introduced a checksum that would record the sum of each row, implying the number of anomalous data points at each corresponding time instance. So for example, in the first row as you see, the checksum 3 implies that at the T3th instance, there are 3 anomalous data points that have been recorded simultaneously by the sensor IDs. We then identified the groups of consecutive rows in the matrix with a checksum greater than 1. And this is because we assumed that a leakage would imply anomaly in at least 2 sensors at either end of the pipe. So in this case, as you see, the third row, the fourth row, the fifth row, and the sixth row, which are fundamentally T6 through T9, are the consecutive timestamps against which we have found a checksum of greater than 1, which is highlighted in blue. And then for each of these checksums, we listed the nodes whose anomalous readings contributed to the corresponding checksum. So for example, in the first checksum in blue, which is 5, this number 5, the checksum 5 was contributed by the 5 different nodes, which are C1, C7, C8, C9, and C10 respectively, which is highlighted in green. We then computed all possible combinations of these sensor IDs and discarded the invalid combinations by cross-referencing the combinations with the ones saved in the in-memory master map. So basically, we compared the values of the combinations from the combinations that was initially created while we prepared this in-memory master map. And using this master map, we then mapped the link IDs corresponding to these valid sensor ID combinations. So we got the pipe IDs associated with the valid sensor node combinations by cross-referencing with the in-memory master map that we had created in step 2. We then executed an emitter-based leakage simulation for pressure-dependent demand, commonly known as PDD, where a possible leakage is implied by a significant difference between the best demand and the actual demand. To localize the leaked pipe, we considered the pipe amongst this list of pipes that had the maximum difference between the base and actual demands. And the first occurrence of each leakage was implied by the minimum value of the timestamp corresponding to each of the successive anomalous timestamp-based groups. And this was how our solution was designed to identify and localize the leakages in the water network. In our next slide, we show the leakage analysis of 2018 and 2019, where we tested the solution for on the 2018 data to identify when each leakage had first occurred. And for these two instances, which with negative values you see in this blue rectangle, we concluded that the first instance of leakage did not happen in 2018, but it happened prior, that is, probably in 2017. And on the right, what you see here is our result set for the identification of the leakages in 2019. And that's all about our solution approach. Next, we wanted to talk about why we chose a deterministic approach over a probabilistic one. Well, the two major reasons that led us to choose this deterministic approach over a probabilistic one are: one, we did not have information about accuracy or precision of the sensors, and if any service maintenance downtime for a sensor would lead to a false anomalous reading. And two, anomaly detection algorithms like isolation forests, as shown in this case on your right, reflect anomalies based on the contamination parameter, which takes into consideration the outlier fraction. So increasing or decreasing this value would increase or decrease the anomalous data points as highlighted by the red dots, from which identification of a true anomaly would be a challenge for us. To conclude, we would like to mention that with the 2019 data not reflecting a steady fixing of its water leakages unlike 2018, our algorithm recorded 12 leakage instances, most of which evidently occurred due to some major incident in the network during mid of May 2019. And most of these leakages originated during the morning hours between 7:30 and 8 o'clock. With this, as we conclude our presentation, we would like to convey that we continue our improvement of the solution by including more features from the world of hydraulics engineering. Well, we sincerely thank you for accepting our solution and for enabling us with this opportunity to showcase our solution with all the jury and the participants of the Battle Challenge 2020. Stay healthy and safe. Thank you.